The universe is not a still picture but a living story, written by invisible hands of immense power. From the explosive birth of everything to the silent drift of galaxies, each moment is shaped by fundamental forces and phenomena. This is a journey through the 30 most critical engines of cosmic change, the architects of reality itself. By the end, you will understand the fundamental blueprint of creation, the hidden rules that dictate everything from the smallest particle to the largest structure in existence. What if the push that started it all is still stretching space today? What unseen scaffolding holds the stars in place? The cosmos is a grand machine, and we are about to trace every moving part. What part of this cosmic story feels most mysterious to you right now? That first moment defies everything we know about physics. It was not a point in space, but the point where space and time themselves began. Think of it as the first frame of a film that has been playing for nearly 14 billion years, a single instant of creation from which every galaxy, star, and planet would later emerge. This was the Big Bang, the primordial catalyst. All the energy and matter that would ever exist was compressed into an unimaginably hot, dense state, and then space itself began to stretch and cool at a rate that is almost impossible to comprehend. In a fraction of a second, the universe inflated from smaller than a proton to the size of a grapefruit, seeding the entire cosmos with tiny quantum fluctuations. These imperfections, as Stephen Hawking observed, were the necessary flaws in the fabric of reality. Without them, matter would have been spread perfectly smooth, and stars and galaxies could never have clumped together from the formless haze. As the expansion continued, energy condensed into the first particles, and light finally broke free, leaving behind a faint glow that we can still detect today as the cosmic microwave background. This is the afterglow of creation, a baby picture of the universe. So how does a single event from the dawn of time still shape our reality? Because the expansion it started never truly stopped. The universe is still stretching, carrying the echoes of that first moment into the future, setting the stage for the next great force to take the lead. That initial expansion was just the beginning of the story. For a fleeting instant, a fraction of a second so small it has no name in human language, the infant universe did something truly bizarre. It did not just expand, it hyperinflated. Space itself stretched faster than light could ever hope to travel, ballooning from a quantum speck to a volume larger than our entire observable universe today. This is cosmic inflation, a growth spurt of such staggering violence that it ironed out the fabric of reality. Before inflation, the cosmos could have been a twisted, knotted mess of wildly different energies and temperatures. But this exponential stretch smoothed it all out, like pulling on a crumpled sheet until it lies perfectly flat. This is why, when we look out in any direction, the universe appears so remarkably uniform on the grandest scales. Distant regions that should have never been in contact somehow share the exact same temperature, a cosmic mystery that inflation elegantly solves. It tells us that these far-flung places were once neighbors, pressed together before the great stretch tore them apart. But inflation did more than just tidy up the cosmos. It also planted the most important seeds of all. The violent stretching amplified tiny quantum jitters, the kind that exist even in a vacuum, and blew them up to cosmic proportions. These minute ripples in density, these imperfections frozen into the fabric of space-time, became the gravitational blueprints for everything to come. They were the slight over-densities where matter would later feel a stronger pull, the subtle valleys where it would pool. Without that brief, impossible burst of growth, the universe might have remained a formless, featureless sea of particles. Instead, inflation gave it a subtle texture, a whisper of structure that gravity would spend billions of years sculpting into the magnificent tapestry of galaxies we see today. So what force was powerful enough to sculpt the very canvas of creation from those faint whispers? That power has been shaping cosmic destiny from the very first moment matter existed. From those faint whispers in the newborn cosmos, a slow, patient power began to gather its strength. This is gravity, the master architect of the universe. That gentle tug holding you to Earth is the same force that binds galaxies into glittering islands and pulls entire clusters of them across billions of light years. Yet for all its cosmic dominance, gravity is profoundly humble. It is the weakest of nature's four fundamental forces, easily overwhelmed by the push of a magnet or the bonds in an atom. Its power lies not in strength but in persistence and range. While other forces fade quickly, gravity's influence stretches across infinity, accumulating over vast distances to become the great sculptor of the cosmos. Albert Einstein revealed its true nature not as a simple pull, but as a bending of the very stage of reality. His general theory of relativity showed us that mass and energy curve the fabric of spacetime itself. Picture a stretched rubber sheet. Place a heavy bowling ball in the center, and it creates a deep well. Roll a marble nearby, and it will spiral inward, not because of a mysterious force, but because it is following the curved geometry of the sheet. The Earth orbits the Sun not because the Sun is pulling on it like a string, but because our star's immense mass has carved a valley in spacetime, and our planet is simply rolling along the contours of that valley. This curvature is gravity. It dictates the paths of planets, bends the very light from distant stars, and sets the rhythm of cosmic time. After inflation's great stretch, the universe was a nearly smooth soup of particles, but seeded with those tiny density ripples. Gravity went to work on these imperfections with relentless patience. Wherever there was a slightly denser knot of matter, its gravity was a tiny bit stronger. This attracted more matter from the surrounding haze, which made the knot denser and its gravity stronger still, pulling in even more material. It was a snowball effect on a cosmic scale, a feedback loop of attraction that transformed faint whispers into mighty shouts. Over hundreds of millions of years, these gathering clouds of gas collapsed under their own weight, heating up until nuclear fusion ignited in their cores. The first stars burst into light, their birth heralded by gravity's silent, persistent work. This force builds all the structure we cherish. It holds our Milky Way together, orchestrating the stately dance of hundreds of billions of stars around a central hub. It forges the majestic spiral arms of galaxies and binds galaxies themselves into groups, then clusters, and finally immense superclusters that trace a vast cosmic web across the void. And in its most extreme triumph, gravity can also craft a perfect prison. When a massive star exhausts its fuel, its core collapses catastrophically. If the remnant is dense enough, gravity wins a final, absolute victory. It crushes matter past a point of no return, creating a region where spacetime curves so severely that not even light can escape. A black hole is born, a monument to gravity's ultimate power. Yet for all its creative might, gravity is solely an attractive force. It only pulls, it never pushes. And when astronomers began to map the universe on its grandest scales, they found something deeply puzzling. Everything was moving, but the story gravity alone was telling did not match the evidence written in the stars. The cosmos appeared to be flying apart in a way that gravity's relentless pull should have been slowing down. The master architect seemed to be missing a crucial part of its blueprint, hinting at a mysterious counterpart working in the shadows. What invisible hand could possibly be strong enough to oppose the pull of all creation? The master architect of gravity seemed to be missing a crucial part of its blueprint, but the truth was far stranger. Gravity was not working alone. Across the cosmos, there is an invisible framework, a hidden scaffolding that holds the very shape of reality together. We know it exists not because we can see it, but because of what it does to the things we can see. Take a majestic spiral galaxy, for instance, a vast pinwheel of billions of stars. According to the laws of gravity and motion, the stars on the outer edges of that spiral should be moving much slower than those near the bright, dense center. Think of our own solar system, where distant Pluto crawls along its orbit while Mercury whips around the Sun. Yet when astronomers measured the speeds of stars in distant galaxies, they found something astonishing. Stars far from the galactic center were orbiting just as fast as those near it. The entire galaxy was spinning so rapidly that the visible matter, all those glittering stars and glowing gas clouds, simply did not provide enough gravitational glue to hold it together. By all rights, these outer stars should have been flung off into the darkness, like children on an out-of-control merry-go-round. They were not. Something else was there, providing an immense, unseen gravitational anchor. That something is dark matter. Dark matter is a profound cosmic mystery. It does not shine like a star, glow like a nebula, or cast a shadow. It does not emit, absorb, or reflect any form of light or radiation we can detect. It is utterly dark to every telescope we have ever built. We only know it is there because of its gravitational handshake with the ordinary matter we can see. Its ghostly pull bends the very fabric of spacetime, and we can witness that bending. When light from a distant galaxy travels toward us, it follows the curves in spacetime. If a massive cluster of galaxies lies in between, the cluster's gravity, dominated by dark matter, acts like a giant cosmic lens. It warps and magnifies the light from the galaxy behind it, sometimes splitting its image into multiple arcs and strange, distorted shapes. This phenomenon, called gravitational lensing, allows us to literally map the distribution of this invisible mass. We can see where the dark matter is by watching how it bends the light from objects far beyond it. The maps we create reveal that dark matter forms an immense, diffuse halo around every galaxy, extending far beyond its visible edge. It is the hidden skeleton upon which the luminous flesh of stars is draped. This invisible component is not a minor detail. It makes up roughly 27% of the entire mass and energy content of the universe. Ordinary matter, the stuff of planets, stars, and you and me, accounts for less than 5%. Dark matter is the dominant gravitational force in the cosmos on large scales. Without its relentless, patient pull in the early universe, ordinary matter would never have clumped together efficiently enough to form the first galaxies. The slight density ripples from inflation would have been too weak. Dark matter acted as the gravitational well, the deep pit that gathered the diffuse hydrogen and helium gas. It provided the cosmic infrastructure, the scaffolding that allowed the brilliant structures of the universe to be built. Its exact nature, however, remains one of the greatest puzzles in all of science. Is it a sea of exotic, undiscovered particles that barely interact with anything except through gravity? Is it something even more unusual, a flaw in our understanding of gravity itself? We do not yet know, but its gravitational influence is undeniable, the silent partner to every galaxy, the unseen architect of the cosmic web. Yet if dark matter's gravity holds the universe together, what explains the fact that the universe is not just holding together, but flying apart at an ever-increasing rate? The scaffolding is firm, but the stage itself is stretching in a way that defies all expectation, driven by a force even more enigmatic than the darkness. The scaffolding of dark matter holds the universe together, but the stage it is built upon is stretching in a way that defies all expectation. For most of scientific history, we believed the cosmic expansion that began with the Big Bang was gradually slowing down, thanks to the relentless collective pull of gravity from all the matter in the universe. It was a reasonable assumption, Throw a ball into the air and Earth's gravity pulls it back down. The gravitational attraction of billions of galaxies should, over cosmic time, be putting the brakes on the universe's great outward rush. Then, in the late 1990s, two independent teams of astronomers made a shocking discovery while studying distant stellar explosions called Type 1, a supernova. These supernovae are cosmic standard candles, meaning we know their intrinsic brightness. By measuring how dim they appear from Earth, we can calculate their distance with remarkable precision. And by examining the color of their light, we can determine how much the universe has stretched since that light began its journey to us, a measure of how fast the expansion was happening in the past. The researchers expected to see that supernova from billions of years ago, when the universe was younger, showed signs of a faster expansion that had since been slowed by gravity. Instead, they found the opposite. The distant, ancient explosions were dimmer than they should have been. This meant they were farther away than our models predicted. The only explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious repulsive force was working against gravity's pull, pushing galaxies apart at an ever-increasing rate. This discovery, which earned the Nobel Prize in Physics in 2011, unveiled the dominant component of our cosmos, dark energy. We do not know what dark energy is. We only know what it does. It appears to be a property of empty space itself, a kind of anti-gravity woven into the vacuum. According to our best measurements, it constitutes roughly 68% of the total mass and energy budget of the universe. Dark matter, for all its mystery, makes up about 27%. The ordinary matter of stars, planets, and life, everything we see and touch and are made of, accounts for less than 5%. Dark energy is the overwhelming majority of reality, and it is in control. One leading idea is that dark energy is Albert Einstein's cosmological constant, a gentle, repulsive force intrinsic to space. As the universe expands and more space comes into existence, more of this repulsive energy appears, causing the expansion to accelerate further in a runaway feedback loop. Another possibility is that it is a dynamic field nicknamed quintessence that could change over time. Regardless of its true nature, dark energy dictates the ultimate fate of our cosmos. If it continues to dominate, as all evidence suggests it will, the universe is headed for what cosmologists call the Big Freeze or heat death. Over trillions of years, the accelerating expansion will pull all galaxies beyond one another's cosmic horizons. The night sky in the far future of any surviving world will grow utterly, permanently black as every other island universe vanishes over the edge of observable space. It is a lonely, silent destiny written by this enigmatic force. Yet to understand how we arrived at a universe filled with such strange and dominant energies, we must rewind the clock to its earliest, most furious moments, when the fundamental ingredients of reality were first forged. The profound mysteries of dark matter and dark energy are written into the fabric of our present cosmos, but to understand their origin, we must journey back to a time before atoms, before stars, even before the forces of nature as we know them existed. In the universe's first unimaginable moments, the cosmos was not just hotter and denser, it was fundamentally simpler. The four forces that govern our reality today were not four at all. They were one. This is the profound idea of unification, a cornerstone of theoretical physics that suggests the electromagnetic, weak nuclear, strong nuclear, and gravitational forces were once indistinguishable, merged into a single, unified interaction. Think of it like water. At high temperatures, water is a uniform liquid, but as it cools, it can undergo a phase transition, crystallizing into ice with a distinct, rigid structure. The universe underwent similar cosmic phase transitions as it expanded and cooled from its fiery birth. In that first searing fraction of a second, energy was so intense that the forces we consider separate today were perfectly symmetric, blended together. There was no distinction between the force that binds atoms and the force that governs radioactive decay. They were the same thing. Then, as the temperature plummeted, the universe crossed a critical threshold. This perfect symmetry broke. The single, unified force split or froze out into different identities. The first to peel away was gravity, retreating into its own realm of curved spacetime. An instant later, the strong nuclear force, the incredibly powerful glue that holds atomic nuclei together, separated out. What remained was a unified electroweak force. This is not just speculation. Particle accelerators like the Large Hadron Collider have recreated the staggering energies of the early universe, providing direct evidence for this merger. They have shown that at energies above a certain point, the electromagnetic force which governs light and chemistry, and the weak nuclear force responsible for certain kinds of radioactive decay become one and the same. They are two facets of a single coin, revealed only when we smash particles together with enough violence to strip away the low-energy reality we inhabit. This sequential separation of forces, this cosmic freezing, dictated everything that came next. It set the fundamental rules for what kinds of particles could exist and how they could interact. It determined the stability of matter and the very possibility of atomic nuclei. If the strong force had been slightly weaker, protons could never have stuck together, and complex elements would be impossible. If the electroweak symmetry had broken differently, atoms themselves might not be stable. The universe we see is a direct consequence of how and when these forces chose their separate paths. This primordial unity, hidden now beneath the cool, structured reality we experience, is the reason our cosmos has the particular set of physical laws that allowed for galaxies, planets, and life to eventually emerge. But these laws required raw materials to work with. The forces needed something to act upon, particles born from the very energy of the young universe. The universe's fundamental forces set the stage, but they needed a cast of characters to bring the cosmic story to life. Within the heart of an atom's nucleus, a silent, titanic struggle unfolds every moment. Protons, each carrying a positive electric charge, should violently repel each other, blasting the nucleus apart in an instant. Yet they do not. They are held together by the strongest glue in all of nature, a force that overpowers the electromagnetic repulsion with ease. This is the strong nuclear force, the atomic glue that makes matter possible. Its strength is almost beyond comprehension, more than 100 times stronger than the electromagnetic force at these tiny scales. But this immense power comes with a critical limitation, a vanishingly short leash. The strong force operates only over a distance roughly equal to the width of a single proton. Step beyond that minuscule boundary and its influence drops to almost nothing. This is why the nucleus of an atom is so incredibly compact, and why you do not feel a pull from the nucleus of a chair when you sit down. Its power is locked away, confined to the deepest interior of matter. This force actually works on two levels, a beautiful hierarchy of binding. At the most fundamental level, the strong force is mediated by particles called gluons, which act as the carriers of this intense attraction. Their job is to bind together the elementary particles known as quarks. You cannot have a single quark alone in nature. They are always found in groups, held in permanent confinement by a torrent of gluons. 3 quarks bound together by the strong force form a proton or a neutron, the building blocks of atomic nuclei. But the force's work does not stop there. A residual effect of this quark-level binding spills over, creating an attraction between the protons and neutrons themselves. This residual strong force is what overcomes the fierce electrical repulsion between protons, cementing them alongside neutrons into a stable, dense cluster, the atomic nucleus. Without this dual action, protons would never stick together. there would be no elements heavier than hydrogen, which is just a single proton, no carbon, no oxygen, no iron. The universe would be a boring, featureless sea of hydrogen atoms, with no possibility for stars, planets, or the chemistry of life. This force does not just build matter, it also powers the stars. The stability it provides inside a nucleus is what makes nuclear fusion possible. In the crushing heat and pressure of a star's core, hydrogen nuclei, which are single protons, are forced together. The strong force must overcome their natural repulsion to fuse them, creating a helium nucleus and releasing a tiny amount of energy in the process. Multiply this event by countless trillions happening every second in a star's heart, and you have the engine that lights up the cosmos. Every photon of sunlight that warms the Earth began with the strong nuclear force winning a microscopic battle against electromagnetism. It is the ultimate alchemist, forging the heavier elements in stellar furnaces, and in the violent explosions of supernovae, scattering them across space to become the raw material for new worlds. Yet this bedrock of stability is not absolute. For the universe to achieve the complex balance we see, another, more subtle force must also be at work, one that allows for change and transformation over cosmic time. But stability alone cannot build a complex cosmos. For that, you need change. While the strong nuclear force acts as the unbreakable glue, holding atomic nuclei together with immense power, another force works quietly in the background as the universe's great alchemist. This is the weak nuclear force, the subtle agent of transformation. It is the reason stars shine and the key to why our universe is made of matter at all. Unlike the strong force with its short, powerful grip, the weak force operates over an even smaller distance and is, as its name suggests, vastly weaker. Its influence is not about holding things together, but about allowing them to become something else. The most familiar example of its work is a process called radioactive beta decay. Inside an unstable atomic nucleus, a neutron cannot hold its form. Through the action of the weak force, that neutron spontaneously transforms. It changes into a proton while simultaneously spitting out an electron and an almost ghostly particle called an antineutrino. In that single subatomic event, one element has subtly shifted toward another. This transformative power is not just a curiosity of unstable rocks, it is the heart of stellar engines. In our Sun, the primary fusion process that turns hydrogen into helium relies on the weak force at a critical step. When two protons collide in the solar core, the intense heat and pressure are not quite enough to overcome their mutual repulsion for a direct fusion. Instead, through the weak force, one of those protons can transform into a neutron, allowing the new proton-neutron pair to bind together into a deuterium nucleus. This is the slow, bottleneck step in the solar fusion chain. Without the weak force's ability to change a proton's very identity, stars like our Sun would flicker out, unable to ignite their primary fuel. This force was even more crucial in the first few minutes after the Big Bang, during the era of primordial nucleosynthesis. As the universe cooled from a soup of free particles, the weak force governed the delicate dance between protons and neutrons, constantly converting one into the other. Its strength and the rate of the universe's expansion froze in a specific ratio, leaving behind roughly 7 protons for every 1 neutron. This ratio directly determined how much of the early universe condensed into helium versus hydrogen, setting the initial chemical makeup for everything to come. But the weak force holds a deeper, more mysterious secret. It is the only force in nature that cares about handedness. In a profound violation of what physicists call parity symmetry, the weak force interacts differently with particles spinning in a left-handed direction compared to those spinning to the right. This intrinsic bias, this preference for left over right at the most fundamental level, may have been the tiny seed that led to one of the cosmos's greatest mysteries. In the universe's earliest, most energetic moments, particles and their antimatter counterparts should have been created in perfectly equal amounts. When matter and antimatter meet, they annihilate in a flash of pure energy. An equal creation should have led to total annihilation, leaving behind a universe of light and nothing else. Yet here we are in a cosmos made almost entirely of matter. The weak force's subtle left-handed bias might have provided a slight tipping of the scales, favoring the production or survival of matter over antimatter by just 1 part in a billion. That minuscule asymmetry was enough. Everything we see, from the farthest galaxy to the ground beneath our feet, is the leftover residue from that ancient, lopsided battle. The weak force, this quiet agent of change, did not just forge the first elements. It may have ensured there was something here to be forged at all. And the forge where these elements are perfected requires conditions of unimaginable violence. The subtle transformations of the weak force forged the first atomic seeds, but for a universe of structure and light, those seeds needed a master architect of connection. This is the role of electromagnetism, the weaver of light and matter. It is the force you experience every single day, from the warmth of sunlight on your skin to the solidity of the floor beneath your feet. While gravity sculpts the large-scale architecture of the cosmos, and the nuclear forces operate in hidden, microscopic realms, electromagnetism is the force that builds the tangible world in between. It governs the interaction between anything with an electric charge, from the subatomic dance of electrons around a nucleus to the vast magnetic fields that cradle galaxies. Its rules are elegantly captured in James Clerk Maxwell's equations, a set of 4 mathematical statements that unified electricity, magnetism, and light into a single, breathtaking theory. Maxwell showed that light itself is a self-propagating wave of oscillating electric and magnetic fields, an electromagnetic ripple traveling through the fabric of space. This revelation was monumental. It meant that the glow of a star, the colors of a rainbow, and the invisible signals from a radio tower are all the same phenomenon, just vibrating at different frequencies. At the quantum level, this interaction is refined by quantum electrodynamics, which describes how charged particles like electrons and protons communicate by exchanging tiny packets of energy called photons, the fundamental particles of light. This force is the reason atoms hold together. The negatively charged electrons are bound to the positively charged nucleus by this powerful electromagnetic attraction. The specific arrangement of these electrons, their orbits and energy levels, defines an element's chemical personality. It is why carbon can form the long chains of life, why oxygen binds with hydrogen to make water, and why iron has the strength to build civilizations. The entire periodic table and all the chemistry that springs from it is a direct manifestation of electromagnetic law. In the cosmos, electromagnetism is our primary window on the universe. Every photon that reaches our telescopes, whether it is a radio wave from a distant quasar, an X-ray from a supernova remnant, or a visible photon from a neighboring star, is a messenger governed by this force. It carries encoded information about temperature, composition, magnetic fields, and motion across the void. This force also shapes cosmic environments with visible drama. Inside stars, it governs the behavior of searing plasma, the fourth state of matter where atoms are ripped apart into a soup of charged particles. The churning of this plasma can generate immense magnetic fields that loop and twist, sometimes snapping in colossal solar flares. Around planets like Earth, our planet's molten core generates a global magnetic field, a protective bubble called the magnetosphere. This invisible shield deflects the relentless stream of charged particles from the solar wind, channeling some toward the poles where they collide with the atmosphere to create the shimmering curtains of the auroras. Electromagnetism builds the intricate, stable structures that make our reality rich and complex. But these structures, from the water in a cell to the iron in a star, are not elemental. They are built from simpler ingredients fused together under immense pressure and heat. For matter to ascend from simple hydrogen to the complexity we see, it requires a cosmic forge of unimaginable power and violence. The cosmic forge where elements are born is a place of unimaginable pressure and heat. This is nucleosynthesis, the grand alchemical process that transforms the universe's simple beginnings into the rich chemical tapestry we see today. It did not happen all at once, but in 3 distinct acts, each more dramatic than the last. The opening scene played out in the first 3 minutes after the Big Bang, in a fleeting era known as Big Bang nucleosynthesis. The entire cosmos was still a searing, dense soup of protons and neutrons zipping about at fantastic speeds. As it expanded and cooled, these particles began to stick together. Protons and neutrons fused into the nuclei of the lightest elements. For every 1 neutron, about 7 protons were available, a ratio set by the earlier action of the weak nuclear force. This simple math dictated the outcome. Vast amounts of hydrogen, which is just a single proton, were locked in. Pairs fused to form helium, capturing nearly all the available neutrons. Trace amounts of lithium and beryllium were also created, but nothing heavier. The universe's first chemical composition was set: 75% hydrogen, 25% helium, and a tiny sprinkling of lithium. For hundreds of millions of years, that was all there was, a cosmos of 2 simple gases waiting for a new kind of furnace to ignite. That furnace is a star. Inside the crushing core of a star like our Sun, the first act of stellar alchemy begins. Under gravity's immense pressure, temperatures soar to millions of degrees. Hydrogen nuclei, those single protons, are slammed together with such force that they overcome their natural repulsion. Through a multi-step process involving the weak force, they fuse into helium. This fusion releases a tiny burst of energy, and multiplied by countless trillions of reactions every second, it is what makes a star shine. This is the main sequence phase where a star spends most of its life. But the story does not end with helium. When a star exhausts the hydrogen in its core, the core contracts under gravity, heating up even further. Now, temperatures reach over 100 million degrees, hot enough to fuse helium nuclei. 3 helium nuclei can collide to form a carbon nucleus. Add another helium and you get oxygen. This process of successive fusion, called stellar nucleosynthesis, builds elements step by step up the periodic table, creating neon, magnesium, silicon, and others. Each new fuel requires higher temperatures and pressures, and each fusion stage is shorter and more frantic than the last. The star becomes a layered onion with a core of silicon fusing into iron, surrounded by shells of progressively lighter elements. But here at iron, the star's peaceful alchemy hits a wall. Fusing iron does not release energy, it consumes it. Iron is the most stable nucleus, the ash of stellar fusion. With the creation of an iron core, the star's energy production shuts off. Gravity, no longer balanced by outward pressure from fusion, wins instantly and catastrophically. The core collapses in less than a second. This triggers the star's final, spectacular performance, a supernova. In that unimaginable explosion, temperatures and pressures spike to levels never seen in the star's quiet life. A storm of neutrons floods the dying core. In a furious process called rapid neutron capture, atomic nuclei are bombarded by neutrons faster than they can radioactively decay. This builds the heaviest elements in the universe, everything beyond iron on the periodic table. Gold, silver, platinum, uranium, the iodine in your body, the xenon in a car's headlight. All of it is forged in these few seconds of stellar death or in the equally violent collisions of neutron stars. The supernova then does one more vital thing. It blasts these newly forged elements out into the surrounding space at nearly 1/10 the speed of light, enriching vast clouds of gas and dust. We are literally stardust, the calcium in your bones, the oxygen you breathe, the carbon that forms the backbone of every organic molecule. All were cooked in the heart of a long-dead star and scattered by its explosive end. This cosmic recycling is continuous. Those enriched clouds, now seeded with the elements for rock, metal, and complex chemistry, will eventually collapse under gravity to form a new generation of stars, this time surrounded by planets. With the raw materials now scattered across the galaxy, the stage is set for gravity's most delicate work, pulling these diverse elements together into stable, complex structures where entirely new possibilities can emerge. For a star to shine for billions of years, it must achieve a perfect dynamic standoff. Deep within its core, the crushing weight of its own mass, the relentless pull of gravity, is constantly trying to collapse the entire structure inward. Pushing back against this immense pressure is not a solid surface, but an invisible force born from light itself. This is radiation pressure, the stellar balancer. Every photon of light generated by nuclear fusion in the star's heart carries a tiny amount of momentum. As these photons bounce and scatter their way outward through the dense plasma of the star, they exert a gentle but continuous push on the surrounding matter. It is a bit like being in a crowded room where everyone is constantly, gently nudging you toward the exit. This outward push from countless trillions of photons perfectly counteracts the inward crush of gravity, creating a state of hydrostatic equilibrium. This balance is not static, it is a finely tuned feedback loop. If the fusion rate in the core were to increase slightly, more photons would be produced, increasing the radiation pressure. This would cause the star to expand slightly, which cools the core and slows the fusion rate back down. If fusion slowed, radiation pressure would drop. Gravity would gain the upper hand, compressing the core and heating it up again, reigniting fusion. This self-regulating mechanism is what allows a star like our Sun to burn with such steady brilliance for so long. In more massive stars, however, radiation pressure becomes a far more dominant and forceful player. Their cores are so intensely hot and luminous that the sheer torrent of photons creates an outward pressure of staggering strength. This pressure is so powerful that it can actually drive material off the star's surface, creating ferocious stellar winds that stream out into space at millions of miles per hour. These winds strip the star of its own mass, carrying away the very fuel for its fusion furnace and seeding the surrounding space with heavy elements. This mass loss, governed by radiation pressure, directly regulates the star's lifespan and ultimate destiny. It determines how long the star will live, how hot it will burn, and what kind of remnant it will leave behind. The influence of this photon push extends beyond the star itself. In vast clouds of gas and dust, like the beautiful pillars of creation, the intense light from nearby newborn stars exerts radiation pressure on the material. This can sculpt and erode the nebula, carving out intricate shapes and preventing new stars from forming in certain regions by blowing away the raw material they need to grow. Around the most luminous objects in the universe, like quasars, radiation pressure can become so immense that it halts the inward flow of gas entirely, preventing the central black hole from feeding any faster and effectively capping its growth. This force is a testament to the tangible power of light. It is not just something we see, it is something that pushes, shapes, and stabilizes the cosmos. Yet this delicate balance between light and gravity is a temporary truce. The star's life is a race to fuse elements, and every fusion stage is shorter than the last. When the core finally produces iron, the radiation pressure vanishes as iron fusion consumes energy instead of releasing it. In that instant, the balance shatters. Gravity wins its long war, and the star's fate is sealed in a single, catastrophic moment. The star's final act of defiance is its most spectacular. When the core of a massive star fuses its last silicon into iron, the radiation pressure that held gravity at bay for millions of years vanishes in an instant. The balance shatters. In less than a second, gravity wins its long war, and the core collapses at nearly a quarter the speed of light. This is not a gentle fading, but a violent, brilliant death that forges the future of the cosmos. A supernova is the universe's ultimate recycling plant and its most powerful crucible. In that cataclysm, for a few glorious weeks, a single dying star can outshine its entire host galaxy of hundreds of billions of suns. The energy released is almost beyond comprehension, equal to the total output of our Sun over its entire 10 billion-year lifetime, concentrated into a single shattering event. This explosion does two vital things. First, it scatters. The outer layers of the star, now enriched with carbon, oxygen, silicon, and all the elements forged during its life, are blasted outward at speeds approaching 10% the speed of light. This stellar shrapnel, a glowing, expanding shell of heavy elements, seeds vast regions of interstellar space with the raw materials for new worlds. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were forged in a star and delivered by a supernova explosion that occurred billions of years before our solar system was born. Second, and even more crucially, the explosion itself forges. The unimaginable temperatures and pressures in the rebounding shockwave, combined with a flood of neutrons from the collapsing core, create conditions for rapid neutron capture. In these few chaotic seconds, atomic nuclei are bombarded, building elements heavier than iron that could never form in a star's quiet furnace. Gold, silver, platinum, uranium, the iodine in your body, all are minted in these final moments of stellar death. The supernova's work continues long after its light fades. The expanding shockwave, a wall of energy and compressed gas, plows into the surrounding interstellar clouds. Like a snowplow piling up a drift, this shock can compress cool clouds of hydrogen, triggering gravitational collapse and sparking the birth of a new generation of stars. Our own solar system may well have been triggered into existence by the shockwave from a nearby supernova, its violence gifting us the very elements for planets and life. And what remains of the star's core, that fate depends on its mass. For many, the collapse is halted by a quantum rule, creating a neutron star, a city-sized sphere so dense that a single sugar cube of its material would weigh as much as a mountain on Earth. For the most massive stars, no force in the universe can stop the collapse, and a black hole is born. But before it vanishes from view, the supernova performs one last service for science. A specific type, known as a Type 1, a supernova, occurs when a white dwarf star steals enough mass from a companion to trigger a runaway thermonuclear explosion. Because this tipping point is always the same, these explosions have a known standard brightness. They became the cosmic mile markers that, in the late 1990s, revealed the universe's accelerating expansion and the existence of dark energy. These stellar deaths, therefore, are not an end but a brilliant, necessary transformation. They are the universe's method of renewal, scattering the ashes of old stars to become the building blocks of new ones, of planets, and of every complex structure within them. With the galaxy now seeded by these explosions, the next chapter requires a gentler, more patient force to gather those scattered riches and begin construction. The scattered stardust from those ancient supernovae does not drift aimlessly. It is guided by invisible lines of force that weave through the cosmos like cosmic rail tracks. These are magnetic fields, the great conductors of the universe. While gravity sculpts the large-scale architecture, magnetism governs the intricate dance of charged particles, shaping the finer details of cosmic structure. These fields are generated wherever electrically conductive material is in motion. Inside stars and planets, churning molten metal or plasma creates a self-sustaining engine called a dynamo effect. Moving charges generate a magnetic field, and that field, in turn, influences the motion of the charges, perpetuating the cycle. This is how Earth's molten iron core generates our protective magnetosphere, and how the turbulent plasma of our Sun weaves its complex, ever-changing magnetic web. These fields are not local curiosities, they are ubiquitous. They thread through stars, wrap around planets, permeate entire galaxies, and recent observations suggest they may even exist in the vast, seemingly empty spaces between galaxies. Their influence is profound and often visible. On the Sun, tangled magnetic field lines can snap and reconnect in colossal solar flares, releasing energy equivalent to billions of atomic bombs and hurling clouds of charged particles across the solar system. When those particles encounter Earth's magnetic field, they are funneled toward the poles, colliding with our atmosphere to paint the sky with the shimmering curtains of the aurora. But magnetism's role extends far beyond these beautiful displays. In the cold, dark clouds where stars are born, magnetic fields provide crucial pressure support, resisting gravity's pull and slowing the collapse of gas. They channel material along their lines, influencing the rotation and final mass of a newborn star. In galaxies, magnetic fields are woven through the spiral arms, providing a subtle scaffolding that helps shape their majestic form and can even accelerate particles to nearly the speed of light, creating the mysterious cosmic rays that constantly bombard our planet. These fields are the silent organizers of ionized matter, guiding stellar winds, confining plasma, and orchestrating the flow of energy across the cosmos. They remind us that the universe is not just a collection of masses, but a dynamic electromagnetic tapestry, where invisible forces write their signatures in light and motion. And some of that motion, propelled by these very fields, reaches velocities that brush against the ultimate cosmic speed limit. These invisible magnetic highways are not empty. Racing along them, deflected and accelerated by their curves, are the universe's most energetic travelers. Our planet is under a constant, silent rain from deep space. Every second, thousands of these particles, moving at almost the ultimate speed, pass right through your body and everything around you. These are cosmic rays, the high-energy messengers from the most violent events in the cosmos. They are not rays of light but atomic bullets, primarily single protons, the nuclei of hydrogen atoms, stripped of their electrons and hurled across the galaxy at velocities just a hair's breadth shy of the speed of light. Their origins are as dramatic as their journey. They are flung into the void by the very engines we have been discussing. The shock waves from supernova explosions act as natural particle accelerators of staggering scale, their expanding fronts surfing charged particles to incredible energies. Even more powerful sources, like the swirling, superheated disks around supermassive black holes in active galactic nuclei, can launch these particles on intergalactic voyages. When a cosmic ray, carrying the energy of a professionally thrown baseball but compressed into a single subatomic particle, slams into a molecule in Earth's upper atmosphere, it triggers a spectacular cascade. That single high-speed nucleus smashes apart an air molecule, creating a shower of secondary particles, muons, electrons, and gamma rays that rain down toward the surface in a widening cone. This is a constant, natural source of background radiation, and it is the reason that sensitive particle detectors are often built deep underground, where the rock above shields them from this perpetual cosmic drizzle. But these particles are far more than just a natural phenomenon. They are priceless messengers. By catching these particles with ground-based detectors or instruments on high-altitude balloons, scientists can analyze their composition and measure their energy. This data is a forensic report from a cosmic crime scene. The specific mix of elements in cosmic rays, from lightweight lithium and boron to heavier iron nuclei, tells a story about where they have been. The presence of certain rare isotopes like lithium-7 or beryllium-10 is a direct clue. These elements are not made in significant amounts in stars or supernova. Instead, they are forged when a high-energy cosmic ray, like a carbon or oxygen nucleus, smashes into a slow-moving atom of interstellar gas, fragmenting it in a process called spallation. By studying the abundance of these cosmic ray-produced elements, astronomers can map the history of particle traffic through our galactic neighborhood. Most importantly, the incredible energy these particles carry points directly back to their source. Tracing them back across the sky, against the deflections of galactic magnetic fields, is like following the twisted path of a ricochet to find the original gun. They lead us to the most powerful particle accelerators in the universe, the supernova remnants and active galaxies whose magnetic furnaces are capable of feats far beyond anything we can build on Earth. They remind us that the universe is a laboratory of extreme physics, conducting experiments on a scale we can only witness from a distance. And some of the most intense experiments occur where these magnetic fields reach their most extreme concentration, around objects where gravity has achieved its final, absolute victory. Gravity's pull is not always a gentle embrace. When its strength varies dramatically across a single object, it becomes a sculptor of distortion and a source of spectacular violence. These are tidal forces, the gravitational stretch. We experience them daily as the ocean's tides, the gentle, rhythmic rise and fall caused by the moon's differential pull on our planet. The side of Earth facing the moon feels a slightly stronger tug than the side facing away, stretching the global ocean into two subtle bulges. But on a cosmic scale, this same principle can produce effects of breathtaking power. Tidal forces arise from a simple, relentless fact: gravity weakens with distance. If you are falling feet first toward a black hole, the gravitational pull on your feet is significantly stronger than the pull on your head. This difference in force, this gradient, stretches you along the line toward the massive object. For a rigid body like a moon or a planet, this creates a stretching tension. For a loose aggregate like a star or a gas cloud, it can be catastrophic. This is why we see such fascinating arrangements in our solar system. Many moons are tidally locked to their planets, like our own moon is to Earth. The gravitational gradient over eons has stretched and flexed the moon's interior, creating friction that gradually slowed its rotation until it matched its orbital period. Now it forever shows us the same familiar face, a permanent state of gravitational balance. For Jupiter's volcanic moon Io, tidal forces are not a one-time lock but an ongoing torment. As Io orbits, the immense gravity of Jupiter, combined with the rhythmic tugs from neighboring moons Europa and Ganymede, constantly kneads its interior like clay. This tidal flexing generates tremendous internal heat, melting rock and driving the most intense volcanic activity in the entire solar system, painting its surface in brilliant yellows and oranges with sulfurous eruptions. But the ultimate demonstration of tidal power occurs in the most extreme gravitational neighborhoods, when a star, by chance, wanders too close to a supermassive black hole lurking in a galactic center. The star is not simply swallowed whole. Instead, the side facing the black hole is pulled in so much more powerfully than the far side that the star is literally ripped apart in a cataclysm known as a tidal disruption event. The star is stretched into a long, thin strand of superheated plasma before being devoured, lighting up the galactic core with a flare that can outshine the galaxy itself for months. These forces are the fine print in gravity's contract, the dramatic proof that it is not a uniform field but a landscape of steep hills and valleys. They shape the orbits and fates of binary stars, distort galaxies during close encounters, and remind us that in the cosmos, even a force of attraction can, through sheer imbalance, become an agent of spectacular dissolution and change. The grand spirals of galaxies are not frozen pinwheels but living, breathing systems in motion. A spiral arm is not a fixed structure of stars like a painted stripe on a spinning disk. Instead, it is a pattern, a cosmic traffic jam moving through the galactic flow. This is the phenomenon of spiral density waves, a gravitational rhythm that orchestrates the light and life of entire galaxies. Picture a busy highway where, for no apparent reason, traffic suddenly slows to a crawl. Cars enter the slowdown, bunch up tightly, and then eventually speed out the other side. The jam itself is not a collection of the same cars. It is a pattern of compression that moves slowly backward against the traffic. In a spiral galaxy, the traffic is the billions of stars and vast clouds of gas orbiting the galactic center. The gravitational influence of the galaxy's central bar or the pull of a neighboring galaxy can create a standing wave of higher density, a slow-moving pattern of crowded space that plows through the faster orbiting material. As a giant cloud of interstellar gas enters this density wave, it is suddenly squeezed, compressed by the collective gravity of the crowded region. This compression triggers a crisis, forcing the cloud to collapse under its own weight. From that collapse, new stars are born in brilliant blue-white clusters. This is why the spiral arms appear so radiant and defined. They are not arms of old stars, but stellar nurseries, illuminated by the short, fiery lives of massive newborn suns. The stars themselves do not stay in the arm. They are born within the wave, shine brightly for a few million years, and then, as they orbit onward, they leave the pattern behind. The spiral arm is a wave of creation, a temporary zone of intense pressure that lights up with stellar fire as it passes, while the older, longer-lived stars drift in and out of the pattern, tracing the grand design but not defining it. This elegant theory solves a profound mystery. If the arms were made of fixed stars, the galaxy's rotation would wind them up tightly within a few 100 million years, like stirring cream into coffee. Yet we see beautiful, open spirals in galaxies billions of years old. The density wave is the answer. The pattern is stable and self-reinforcing, maintained by gravity itself. The burst of star formation it triggers does not just create light, it enriches the galaxy. The most massive of these new stars live fast and die young, exploding as supernovae within the spiral arm. These explosions seed the surrounding gas with heavy elements, raising the overall metallicity of the galaxy with each rotation. The density wave, therefore, is a regulator. It paces the galaxy's star formation, dictates where new solar systems will be forged, and governs the chemical evolution of its interstellar medium. Yet this beautiful internal clockwork is not immune to outside influence. A close encounter with another galaxy can send disruptive ripples through this delicate gravitational rhythm, distorting the spiral pattern, triggering starbursts, or even transforming the galaxy's entire shape. The dance of the density wave is a balance between internal harmony and the chaotic potential of a changing cosmic environment. The gentle rhythm of a spiral galaxy is a cosmic lullaby compared to the thunderous crashes we can now hear. In September 2015, a signal lasting less than half a second shook the world of physics. It was not a sound or a flash of light, but a tremor in the very stage of reality. A ripple in spacetime itself had washed over Earth, stretching and squeezing our planet by a distance smaller than the width of a single proton. This was a gravitational wave, a phenomenon predicted by Albert Einstein a century earlier and finally witnessed, confirming one of the last great untested pillars of his general relativity. Einstein's genius revealed that gravity is not a mysterious pull, but the curvature of spacetime by mass and energy. His equations also showed that when massive objects accelerate, especially when they whip around each other at incredible speeds, they can create waves in this cosmic fabric. These are not waves of matter or light, but propagating distortions of geometry, traveling outward at the speed of light, compressing space in one direction while stretching it in another as they pass. For decades, they remained purely theoretical. The distortions they cause are so incredibly tiny that detecting them seemed almost impossible. It required events of staggering violence and instruments of exquisite sensitivity. That first detected ripple was born from a catastrophe 1.3 billion light-years away. Two black holes, each roughly 30 times the mass of our Sun, had been locked in a final, frantic dance. Spiraling toward each other at nearly half the speed of light, their immense acceleration pumped enormous energy into the fabric of spacetime, sending out these ripples. In the last fraction of a second before they merged into one larger black hole, the waves reached a crescendo, a chirp that was picked up by the twin detectors of LIGO, the Laser Interferometer Gravitational Wave Observatory. This was a new sense for humanity. For all of history, we have studied the universe by collecting light from radio waves to gamma rays, but light can be blocked, scattered, or absorbed by dust and gas. Gravitational waves pass through almost everything unimpeded. They carry a pure, unaltered fingerprint of the most extreme gravitational events, allowing us to perceive things invisible to traditional telescopes. Since that first detection, we have heard the mergers of many more black hole pairs, and in 2017, a landmark event, the collision of two neutron stars. That collision produced both gravitational waves and a flash of light across the electromagnetic spectrum, from gamma rays to radio waves, allowing us to see and hear the same event for the first time. This confirmed that such collisions are indeed the cosmic forges where heavy elements like gold and platinum are created. We are now listening to the hidden symphony of the universe, a chorus of crashes from the darkest, densest objects. Future observatories in space will tune into lower frequencies, allowing us to hear the even deeper hum of supermassive black holes merging in the hearts of galaxies, and perhaps even the faint echoes from the universe's very first second. This new window reveals a cosmos far more dynamic and violent than we ever imagined, where the fabric of reality itself rings like a bell struck by colliding stars. Even a perfect prison may have a tiny, quantum-sized leak. Stephen Hawking's revolutionary insight was that black holes are not the eternal, featureless graves we once imagined. By applying quantum mechanics to the strange space just outside the event horizon, he discovered they must have a temperature. This phenomenon, Hawking radiation, is a whisper of heat from the coldest places in the universe. It works because of the quantum nature of empty space. The vacuum is not truly empty. It is a seething foam of virtual particle pairs, constantly flickering into and out of existence. Normally, these pairs annihilate each other almost instantly, but at the very edge of a black hole, the gravitational pull is so extreme that one particle of the pair can fall across the event horizon while its partner escapes into space. The escaped particle becomes real radiation, carrying away a tiny amount of energy. To conserve energy, the black hole itself loses a corresponding amount of mass. It is as if the black hole is paying a gravitational tax for this quantum transaction, slowly evaporating from the outside in. This process is unimaginably slow for a stellar mass black hole, taking many times the current age of the universe. But for a tiny, primordial black hole that might have formed in the early cosmos, evaporation could be happening now, potentially ending in a final, tiny flash of energy. Hawking's calculation did more than predict radiation. It forged a profound link between three great pillars of physics: gravity, quantum mechanics, and thermodynamics. It showed that black holes have entropy, a measure of disorder, and that this entropy is proportional to the surface area of its event horizon, not its volume. This suggests that all the information about what fell into a black hole might be encoded on its surface like a hologram, a concept that has reshaped our understanding of information in the universe. The idea of black hole evaporation also hints at a resolution to the famous information paradox. If a black hole evaporates completely, What happens to all the information about the stars, planets, or atoms that fell in? Quantum mechanics says information cannot be destroyed. Hawking radiation provides a potential escape route, suggesting the information might be slowly encoded in the radiation itself, scrambled but not lost, eventually released back into the cosmos. This makes black holes not just endpoints but transformative objects, perhaps the universe's most extreme data processors. The study of their thermodynamics reveals a deep and unexpected connection between the very small, the quantum world, and the very large, the gravitational cosmos. It is a crucial stepping stone toward the holy grail of physics, a unified theory of quantum gravity. While this evaporation is a slow, quiet process, the environments around feeding black holes are anything but quiet, showcasing physics of a much more immediate and violent nature. The energy siphoned from a black hole's meal does not always vanish quietly into the dark. Some of it escapes in the most spectacular way possible, focused into twin beams of pure fury that can pierce the darkness for millions of light years. These are relativistic jets, the universe's ultimate particle accelerators, screaming their existence across the cosmos. They erupt from the poles of supermassive black holes at the hearts of active galaxies, and from some neutron stars as narrow, lightning-fast lances of plasma. The material in these jets is not just hot, it is ionized to its core, a soup of electrons and atomic nuclei stripped bare, and it is hurled outward at velocities so close to the speed of light that the effects of Einstein's relativity become dominant. From our distant perspective, time within the jet appears to slow down, and its brilliance is magnified into a blinding beacon. The power source for this phenomenal eruption is the chaotic feast happening just outside the event horizon. As matter spirals inward in the superheated accretion disk, it does not fall straight in. Intense magnetic fields, wound up by the disk's insane rotation, channel some of this infalling material. Along the black hole's spin axis, the only direction not blocked by the swirling disk, these magnetic fields act like the barrel of a cosmic rifle. They funnel and collimate the plasma, focusing it into two oppositely directed, incredibly narrow beams. This process converts a portion of the gravitational energy released by the infalling matter into the kinetic energy of the jet, a conversion of staggering efficiency. The scale is almost impossible to grasp. These jets can remain tightly focused as they plow through intergalactic space for distances far greater than the size of their host galaxy. We see them in radio telescopes as colossal, diffuse lobes, where the jet finally rams into the thin gas between galaxies and splatters out, depositing its enormous energy into the void. This is where these jets become architects, not just spectacles. The energy they pump into the surrounding galactic environment is a crucial feedback mechanism. It can heat the vast reservoirs of cool gas in a galaxy, preventing that gas from collapsing to form new stars. In this way, a voracious black hole can actually quench star formation in its own home, regulating the galaxy's growth and ultimately limiting the black hole's own future food supply. They are also the source of some of the most energetic particles and photons we detect. The turbulent shocks within these jets are natural accelerators, far more powerful than anything on Earth, capable of boosting particles to energies that make even supernova remnants look tame. They are believed to be the origin of some of the highest energy cosmic rays, and the brilliant flashes of gamma rays we see from blazars, which are galaxies whose jets happen to be pointed almost directly at Earth. Studying these brilliant, destructive fountains helps us understand the intimate and violent relationship between a monster at a galaxy's center and the galaxy's own destiny. The universe's most brilliant particle beams are not just spectacular, they are part of a delicate conversation that shapes entire galactic ecosystems. Galaxies are not isolated islands drifting in silence. They are complex, self-regulating systems where the lives and deaths of their own inhabitants dictate their ultimate fate. This delicate balance is governed by cosmic feedback, a series of push and pull processes that link the smallest stellar events to the grandest galactic structures. Imagine a vast city where every factory's smokestack and every car's exhaust pipe directly control the weather, preventing new factories from being built. In a galaxy, the factories are stars and the central supermassive black hole, and their exhaust is energy. Stellar feedback begins with a gentle but persistent push of radiation pressure and stellar winds from massive young stars. These winds blow like a cosmic gale, carving cavities in the surrounding gas clouds and driving material outward. When these short-lived stars meet their end in supernova explosions, the effect is far more dramatic. These blasts inject enormous energy and heavy elements into the interstellar medium, heating the gas to millions of degrees and often driving it out of the galaxy entirely in powerful galactic winds. This process is a form of negative feedback. By heating and expelling the cool, dense gas required to form new stars, these stellar events effectively put out the very fires that created them. They can quench star formation in a region or even across an entire galaxy, explaining why some galaxies, especially massive ellipticals, are full of old, red stars and have not formed new ones for billions of years. The central black hole contributes its own powerful voice to this conversation through what is known as active galactic nucleus, or a GN, feedback. When the black hole feeds, the resulting relativistic jets and intense radiation blast the surrounding gas with incredible force. This can heat the galactic halo to such extremes that fresh, cool gas cannot flow into fuel future star formation. In the most extreme cases, it can blow away a galaxy's entire reservoir of star-forming material. This is a crucial piece of the cosmic puzzle, explaining why we do not see galaxies growing indefinitely larger and why the growth of the central black hole itself seems to be linked to the mass of its host galaxy's stars. Yet feedback is not always a story of suppression. It can also be positive. The shock waves from a supernova or the expanding shell of a stellar wind can slam into a nearby quiet cloud of gas. Instead of just dispersing it, this sudden compression can trigger gravitational collapse in the cloud's densest regions, sparking a new round of star formation. This creates a beautiful, self-propagating chain reaction, where one generation of stars gives birth to the next along a rippling front, often seen in the glowing shells of so-called superbubbles. These competing loops of creation and destruction are the invisible hands that sculpt the observed diversity of the cosmos. They determine whether a galaxy will be a grand, star-forming spiral, a quiescent red ellipse, or something in between. They link the microphysics of a supernova shockwave to the macro-scale property of a galaxy's shape and size. Without these feedback processes, our models of galaxy evolution simply do not work. Galaxies would form stars too quickly, using up all their gas in a brief, brilliant burst, and they would grow to unrealistic sizes. Feedback provides the necessary thermostat, regulating the pace of cosmic construction over billions of years. And this intricate dance does not happen in a void. It is choreographed within the largest structure of all, the vast cosmic web in which every galaxy is merely a shining knot. The thermostat of galactic feedback operates within a grander architecture, a vast and intricate structure that connects every shining city of stars. This is the cosmic web, the largest pattern in the universe, a delicate filamentary network of dark matter and gas spanning billions of light years. After the Big Bang, the subtle gravitational seeds planted by inflation began their patient work. Dark matter, responding only to gravity, collapsed first into a sprawling, invisible skeleton. Ordinary matter, the gas that would become galaxies, flowed along these dark gravitational rivers, pooling at the intersections where filaments met. The result is a universe that resembles a neural network or a colossal sponge, with immense, nearly empty voids surrounded by walls and threads of condensed matter. The galaxies we see are not scattered randomly like stars in the night sky. They are strung along these luminous filaments, gathered into massive clusters at the nodes, and entirely absent from the dark, cavernous voids in between. This web is not static. It is a dynamic highway system on a cosmic scale. Galaxies are funneled along the filaments toward the dense clusters, drawn in by the immense gravitational pull of these hubs. This slow, stately migration shapes galactic evolution, as galaxies in crowded clusters experience frequent close encounters and mergers, often being stripped of their gas and ceasing star formation. The cosmic web is the ultimate expression of gravity's large-scale work, the final, magnificent structure sculpted from the quantum whispers of the beginning. Yet, if this web is the architecture, what is the nature of the stage it is built upon? The answer lies in the profound and perhaps strangest property of nothingness itself. Empty space is not an inert stage. According to our deepest theories, the vacuum of space is a seething, vibrant sea of potential. Quantum field theory tells us that at the tiniest scales, empty space is alive with transient fluctuations, where particle-antiparticle pairs flicker in and out of existence in a relentless quantum foam. This activity endows the vacuum with a baseline energy density, a fundamental hum of the universe. The simplest mathematical representation of this energy is the cosmological constant, symbolized by the Greek letter lambda. This is not a force in the traditional sense, but a property of space itself, a constant energy density inherent to the vacuum. Its story begins with a famous reconsideration. Albert Einstein introduced the cosmological constant into his equations of general relativity as a fudge factor, a repulsive term needed to achieve a static, unchanging universe, which was the prevailing belief of his time. When Edwin Hubble later discovered the universe was actually expanding, Einstein reportedly called this addition his greatest blunder. Yet, in a stunning twist of cosmic irony, the cosmological constant has been resurrected as the leading explanation for the most surprising discovery of our age, the accelerated expansion of the cosmos driven by dark energy. This vacuum energy exerts a peculiar kind of pressure. While matter and radiation create positive pressure that can slow expansion, the cosmological constant exerts a persistent negative pressure. Think of the vacuum not as empty, but as a kind of springy substance with a sort of internal tension. As the universe expands and new space is created, more of this vacuum energy comes into existence. This new energy exerts its own negative pressure, causing even more expansion in a runaway, self-reinforcing cycle. This is why the expansion of the universe is not just continuing, but speeding up. The value of this constant is incredibly small, but crucially, it is positive. Its observed value is one of the most baffling fine-tuning problems in all of physics. When theorists try to calculate the expected vacuum energy from the sum of all quantum fluctuations, they arrive at a number that is 120 orders of magnitude too large. That is a 1 followed by 120 zeros larger than what we measure. This staggering discrepancy means our understanding is profoundly incomplete, hinting at some exquisite cancellation or a deeper principle we have yet to uncover. The cosmological constant, this gentle but relentless energy of nothingness, writes the final chapter for our cosmos. If it remains the dominant component, as all current evidence suggests, it dictates a cold, silent, and profoundly dark destiny known as the Big Freeze or heat death. As the acceleration continues unabated, distant galaxies will be pushed beyond our cosmic horizon, their light forever too stretched to reach us. The night sky for any surviving observers in the far, far future will grow not just dark, but utterly, permanently black, as every other island universe vanishes over the edge of observable space. Galaxies themselves will be pulled apart, then star systems, and eventually even the bonds holding atoms together may be torn asunder by the relentless stretching of spacetime. It is an end of isolation and stillness, governed by the subtle energy of the vacuum. This pervasive constant stands in stark contrast to the dynamic, changing fields that may have shaped the universe's explosive infancy, suggesting that the properties of space itself have evolved from a state of furious activity to one of calm, dominant persistence. Even the vacuum of space is not truly empty. At the very smallest scales, the universe is a frothing sea of uncertainty, a restless quantum foam where the rules of our everyday reality break down. This turbulence is governed by Werner Heisenberg's famous uncertainty principle, which tells us that for exceedingly brief moments, energy can be borrowed from the vacuum itself. This loan allows for the spontaneous, temporary creation of particle-antiparticle pairs, known as virtual particles. They flash into existence and then almost instantly annihilate each other, returning the energy before the universe can notice the debt. These are not mere mathematical abstractions. They have tangible, measurable effects. Bring two incredibly smooth, neutral metal plates extremely close together in a perfect vacuum. The narrow gap between them restricts which wavelengths of these virtual particle fluctuations can exist there. Outside the plates, the full spectrum of fluctuations pushes inward. This imbalance creates a subtle but detectable force pushing the plates together, known as the Casimir effect. A direct signature of the quantum sees restless energy. We have already seen how this same quantum activity at the edge of a black hole's event horizon leads to Hawking radiation, the slow evaporation of these gravitational giants. But the most profound role of these quantum whispers happened at the very beginning. During the inflationary epoch, when the universe hyperinflated, space stretched faster than light. At that moment, microscopic quantum fluctuations in the field driving inflation, the Inflaton field, were not allowed to simply vanish. Instead, they were stretched along with space itself, blown up from quantum scales to macroscopic, even cosmic proportions. These tiny, random ripples in energy density became frozen into the fabric of the expanding cosmos. They were the subtle overdensities and underdensities, the microscopic hills and valleys that gravity would later use as its blueprint. Every galaxy cluster, every spiral arm, every star, and every planet owes its ultimate origin to these ephemeral quantum jitters. It is a staggering connection, a direct thread linking the bizarre, probabilistic rules of the subatomic world to the grand, gravitational architecture of the entire observable universe. The very largest structures we can see began as the smallest possible disturbances imaginable. This profound insight reveals that the cosmos is not just built on fundamental forces, but on fundamental uncertainty, a cosmic lottery at the quantum scale where we and everything we see are the winning tickets. For these fluctuations to be stretched so perfectly, the universe required a very specific kind of engine, a field with unique properties that could power that incredible burst of growth. That primordial quantum sea needed an engine, a cosmic motor to transform its faint whispers into the blueprint for all creation. This engine is known as the Inflaton field, a hypothetical but profoundly elegant concept that solves the deepest puzzles of our universe's infancy. Picture a vast, gentle hillside covered in a layer of fresh snow. At the very top, a ball rests precariously. This ball represents the state of the Inflaton field in the earliest moments after the Big Bang. The field was trapped in a state of high potential energy, like the ball perched high on the hill. But this was not a stable situation. According to the theory, the field began to slowly roll down this energy hill. And as it did, something extraordinary happened. The energy contained within this rolling field did something we would never expect from ordinary matter or radiation. It caused space itself to stretch at an exponential, faster-than-light rate. This was cosmic inflation powered by the Inflaton field's gradual descent. The field acted as a kind of anti-gravity fuel, its potential energy driving the hyper-expansion that smoothed and flattened the entire observable cosmos. This slow roll was critical. It lasted for a tiny fraction of a second, but that was enough for the universe to inflate by a factor of at least 10 to the power of 26. The field's specific properties, the shape of its hill, dictated everything about this burst: how long it lasted, how much it stretched, and most importantly, what kind of quantum imperfections got frozen into the fabric of spacetime. Then the field reached the bottom of the hill. Its journey was over, but its work was just beginning. No longer held in that high-energy state, the inflaton field began to oscillate wildly around the minimum, like a ball rolling back and forth in a valley. In this frantic oscillation, the field decayed. All that immense potential energy it had been carrying was suddenly released, transforming into a dense, searing hot soup of fundamental particles and radiation. This moment is known as reheating. It was the true beginning of the hot Big Bang era as we traditionally imagine it, a universe filled with a blazing plasma of quarks, gluons, and leptons. The inflaton field had handed off the baton, converting its energy into the raw material for everything to come. While we have not directly detected this field, its theoretical footprint is everywhere. The predictions made by models that include an inflaton field match our observations of the cosmos with stunning precision. The nearly perfect uniformity of the cosmic microwave background, the specific pattern of tiny temperature fluctuations within it, and the flat geometry of space itself are all exactly what a period of inflation driven by such a field would produce. It represents a beautiful bridge between the world of the incredibly small, high-energy particle physics and the incredibly large, the realm of cosmology. Its decay filled the universe with light and matter, setting the stage for the next critical transition, when those frenetic particles would cool enough to combine into the first stable, long-lived building blocks of matter. Our universe is built from a profound and necessary accident. The laws of physics, as we understand them, appear perfectly symmetric between matter and antimatter. For every particle, there should be an antiparticle, a mirror twin with opposite charge. When they meet, they annihilate in a flash of pure energy. According to this elegant symmetry, the Big Bang should have created exactly equal amounts of both. And if that had happened, every particle of matter would have found its antimatter counterpart. The result would have been total, mutual annihilation, leaving behind a cosmos filled only with light and radiation, a featureless sea of photons expanding forever into darkness. Yet here we are, in a universe filled with planets, stars, and galaxies, all made of matter. Something tipped the scales. This monumental puzzle is known as baryogenesis, the genesis of baryons, the family of particles that includes protons and neutrons. It is the story of how our cosmos escaped total cancellation to become a place where solid things can exist. The solution required a set of very specific conditions, first articulated by the physicist Andrei Sakharov. First, there had to be a process that could change the total number of matter particles, violating what physicists call baryon number conservation. Second, the symmetry between matter and antimatter had to be broken, not just once but twice. The laws had to treat particles and their mirror images differently, violating what is known as C-symmetry, and they also had to treat particles differently when their charges and spatial coordinates were all flipped, violating CP symmetry. Finally, these processes could not happen in a calm, settled state. They required the universe to be out of thermal equilibrium, undergoing a rapid, dramatic change. Think of it like freezing a pond. If you cool water very slowly and evenly, it can become supercooled, remaining liquid below its freezing point. But if you disturb it, ice crystals form rapidly in a non-equilibrium phase transition, creating a structured solid from a uniform liquid. The early universe likely provided just such a dramatic setting. One prime candidate moment was during electroweak symmetry breaking, when the electromagnetic and weak nuclear forces split apart. The frantic churning of fields during this cosmic phase transition could have created the right out-of-equilibrium conditions for Sakharov's criteria to be met. Through processes we are still working to understand, these conditions produced a tiny, almost negligible bias. For every 1 billion pairs of matter and antimatter particles that annihilated perfectly, a single extra matter particle was left behind. 1 in a billion, that minuscule surplus is everything. All the galaxies, stars, planets, and life that we see are made from that 1 part in a billion residue, the ashes of an ancient, nearly perfect annihilation. The precise mechanism remains one of the greatest open questions in physics. Experiments like the Large Hadron Collider are searching for signs of the required symmetry violations, and observations of the cosmic microwave background provide clues about the timing of this event. But the outcome is undeniable. Without that slight, mysterious lopsidedness in the laws of nature, the universe would be a dark, empty void. Every atom in your body is a testament to a broken symmetry that happened in the first fleeting instance of time, a cosmic accident that made all subsequent structure possible. With matter now firmly in charge, the universe could proceed to its next great act of consolidation, cooling from a searing plasma into a neutral, transparent gas. For nearly 400,000 years, the universe was a glowing, impenetrable fog. It was a searing plasma so hot that atoms could not hold together. Electrons, negatively charged, zipped freely through a soup of bare atomic nuclei, primarily protons. Any particle of light, a photon, that tried to travel in this dense medium had no chance. It would immediately crash into a free electron, scattering in a new direction, trapped in a constant, frenetic pinball game. The cosmos was utterly opaque, a brilliant but featureless prison of light. Then a profound quiet descended. As the relentless expansion stretched and cooled the universe, the average energy of particles finally dropped below a critical threshold. Electrons, moving slower now, could be captured by the positively charged protons. They settled into stable orbits, forming the first complete, neutral atoms of hydrogen. This event is called recombination, though it was really the first combination. In that moment, the fog lifted. With electrons now bound securely inside atoms, the highways of space were suddenly cleared. Photons, which had been trapped in the chaotic plasma, were set free. They decoupled from matter and began streaming across the universe in every direction, unimpeded for the first time. That ancient flash of liberation is still with us today. We can detect it as a faint, uniform glow that permeates all of space, the cosmic microwave background radiation. It is the afterglow of creation, cooled by billions of years of expansion to just a few degrees above absolute zero. This is not just a static hiss. When we map it with exquisitely sensitive instruments like the Planck satellite, we see it is not perfectly smooth. It is mottled with tiny variations in temperature, minute hot and cold spots that differ by only about 1 part in 100,000. These fluctuations are the fossilized imprints of those primordial quantum whispers from the inflationary epoch, now written across the sky as sound waves frozen in time when the universe became transparent. They are a cosmic treasure map encoding fundamental truths about our reality. By analyzing these patterns, cosmologists can read the composition of the universe, confirming the amounts of ordinary matter, and dark energy. They reveal the geometry of space itself, which appears to be flat to an astonishing degree of precision, just as inflation predicted. This moment of transparency was a cosmic turning point of the highest order. Before recombination, matter was ionized, and the intense pressure from the trapped radiation fought against gravity's pull, preventing structures from collapsing. Now, with the photons gone and matter neutral, gravity finally had the upper hand. The universe became a dark, quiet place, filled with vast clouds of neutral hydrogen and helium gas. The era of light was over, and the long cosmic dark ages had begun. But within that darkness, the subtle seeds of structure were finally free to grow, undisturbed, setting the stage for gravity's patient work to pull the first stars out of the void. The long cosmic dark ages were not a permanent state, but a quiet prelude to a brilliant dawn. After recombination, the universe was a vast, silent sea of neutral hydrogen and helium gas, a featureless expanse where no stars yet shone. For hundreds of millions of years, gravity worked in the darkness, patiently gathering those primordial gas clouds into denser and denser knots. Within these knots, something extraordinary was about to happen. The first protostars ignited, their cores reaching the critical temperature for nuclear fusion. With that ignition, light returned to the cosmos. These were not stars like our sun. They were behemoths, likely hundreds of times more massive, burning ferociously hot and blue, and living fast, violent lives. Their most profound impact was not their visible light, but their intense ultraviolet radiation. This high-energy light acted like a cosmic blowtorch on the surrounding neutral gas. Wherever it streamed out from a newborn star or an early, voracious black hole known as a quasar, it slammed into neutral hydrogen atoms. With enough energy, it could rip the electron clean away from the proton, splitting the atom apart once more. This process is reionization, the universe's second great act of transparency. It began in isolated bubbles around the very first luminous objects. Imagine a dark forest where someone lights a single match. That tiny flame creates a small sphere of light. Now imagine thousands, then millions of matches being struck all across the forest. Their individual spheres of light begin to overlap and merge, pushing back the darkness until the entire woods are illuminated. That is what happened during the epoch of reionization, which unfolded between roughly 150 million and 1 billion years after the Big Bang. Bubbles of ionized plasma, carved out by the radiation from the first stars and galaxies, grew and merged, gradually burning away the pervasive fog of neutral hydrogen. This grand illumination marked the definitive end of the cosmic dark ages and the emergence of the structured, luminous universe we recognize. The energy required for this titanic task was staggering, and it came from the frantic lives and explosive deaths of that first stellar generation. As these massive stars died in supernova, they seeded their surroundings with heavier elements and unleashed shockwaves that further stirred and heated the gas. The reionized intergalactic medium became transparent again, but not to all light. It became clear to most wavelengths, though neutral hydrogen pockets remained in the densest regions, which is why we can still see the faint absorption lines from distant quasars imprinted on their light, like cosmic fingerprints. Studying this era is one of the great challenges of modern astronomy, as it requires peering back to the very edge of observable time. Yet it is crucial, for reionization was not a passive backdrop. It was a feedback process that shaped the formation of the first galaxies themselves. The intense radiation from early stars could heat nearby gas, preventing it from cooling and collapsing to form the next generation of stars nearby, thereby regulating the pace of cosmic construction. This grand clearing of the fog established the essentially transparent intergalactic highway we see today, through which the light from all subsequent galaxies can travel for billions of years to reach our telescopes. It was the universe's final act of preparation, switching on the lights and clearing the stage for the epic, billions-year-long drama of galactic evolution to unfold in plain view. The grand clearing of reionization left the universe transparent, but the real work of building its luminous cities was just beginning. Scattered across the vast galactic landscapes were immense, cold, and silent reservoirs, the raw material for all that would follow. These are molecular clouds, cosmic nurseries where the future is written in dust and gas. Drifting through the spiral arms of galaxies like ours, these clouds are not like the thin, hot plasma between stars. They are dense, frigid, and dark, often spanning dozens of light years and containing the mass of hundreds of thousands of suns. Their composition is simple yet profound, primarily molecular hydrogen, two hydrogen atoms bound together, mingled with traces of other molecules and, crucially, microscopic grains of silicate and carbon dust. This dust is far more than cosmic soot. It is the essential catalyst for star birth. It shields the cloud's interior from the harsh ultraviolet light of nearby stars, allowing the gas to remain cool, only about 10 degrees above absolute zero. And in that profound cold, physics takes a decisive turn. A cloud this massive and cold is a battleground of opposing forces. Gravity, always present, wants to pull every particle inward to collapse the cloud into a dense knot. Pushing back are several formidable opponents. First, there is thermal pressure, the natural outward push of gas particles bouncing off one another. In the cold interior of a molecular cloud, this pressure is minimal, but it is not zero. More significantly, the cloud is threaded with magnetic fields, lines of force that can trap charged particles and provide a kind of magnetic scaffolding, resisting collapse. There is also turbulence, chaotic supersonic motions stirred up by supernova shockwaves or galactic collisions, which churns the cloud and provides additional support. For millions of years, this standoff can persist, the cloud hovering in a fragile equilibrium. But the universe is a place of change. A passing density wave in the galaxy's spiral arm can compress the cloud. A nearby supernova blast can slam into it, or simply the random churning of its own turbulence can create a local pocket of higher density. When that happens, a critical threshold is crossed. This threshold is defined by a concept called the Jeans mass, named for the physicist Sir James Jeans. It is the minimum mass a cloud fragment needs for its self-gravity to overcome all the internal pressures supporting it. Think of it like a game of tug-of-war on a cosmic scale. On one side of the rope, you have the combined strength of thermal pressure, magnetic fields, and turbulence. On the other side, you have the collective pull of the cloud's own gravity. If the cloud fragment is too small and light, the pressure team wins easily, and the fragment simply dissipates or remains puffy. But if a fragment gathers enough mass, its gravitational team becomes overwhelmingly strong. The rope is pulled decisively in one direction, and the balance is shattered forever. At that moment, gravitational collapse becomes inevitable. The fragment, now a prestellar core, begins to fall inward upon itself. This is not a sudden, violent implosion, but a controlled, accelerating descent that can take hundreds of thousands of years. As the core contracts, gravitational potential energy is converted into heat, just like a bicycle pump warms up as you compress the air inside. The temperature at the heart of the collapsing core begins to climb from tens of degrees to thousands, then millions. The core grows denser and hotter, spinning faster as it shrinks, often flattening into a disk that will later form planets. At the center, the conditions become truly extreme. When the temperature soars past about 10 million degrees, protons are moving so furiously that they can overcome their natural electrical repulsion. They slam together, and through the power of the strong nuclear force, they fuse. A proton becomes a neutron, binding with another proton to form a deuterium nucleus, releasing a burst of energy. This is the moment of ignition. Nuclear fusion begins in the core, and a star is born. The outward pressure from this new furnace of light pushes back with tremendous force, halting the gravitational collapse. A new equilibrium is established, and the star will shine steadily for millions or billions of years, its mass determining its lifespan and ultimate fate. But the story of a stellar nursery is not just one of birth, it is also one of self-regulation. The newborn star does not remain a passive resident. Especially if it is a massive, hot star, it immediately begins to influence its own cradle. Its fierce ultraviolet radiation and powerful stellar winds act like a cosmic blowtorch, carving cavities in the surrounding gas and dust. In some cases, this feedback can compress nearby regions of the cloud, triggering the collapse of new cores and sparking more star formation in a chain reaction. In other cases, particularly when the most massive stars end their brief lives in supernova, the feedback is catastrophic. The explosion blasts away the remnants of the parent cloud, dispersing it back into the interstellar medium and effectively shutting down star formation in that region for eons. This beautiful, destructive cycle is the galaxy's primary thermostat. It ensures that stars do not form too quickly, using up all the gas in a single burst. Instead, star formation is paced over billions of years, regulated by the very objects it creates. It is this cycle that converts the pristine, primordial hydrogen and helium from the Big Bang into generations of luminous stars, and through their lives and deaths into the heavy elements essential for planets and life. Every star we see, including our own sun, began in such a cold, dark cloud, a testament to gravity's patience and the transformative power of collapse. And within the swirling disks surrounding these infant stars, an even more intricate process of construction was underway, one that would build the diverse worlds of a solar system. Within that swirling disk of dust and gas around a newborn star, a new act of cosmic construction begins. This is planetary system formation, the delicate process that builds worlds from chaos. The circumstellar disk, a vast, flattened platter of material left over from the star's own birth, is a turbulent construction site on a solar system scale. Tiny dust grains, mere micrometers across, are the first seeds. They drift through the disk, occasionally bumping into one another. In the microgravity of this environment, static electricity and weak molecular forces can make them stick like cosmic Velcro. This is the first step of accretion, a slow gathering that transforms dust into pebbles, pebbles into boulders, and boulders into mountain-sized bodies called planetesimals. As these planetesimals grow, their gravity strengthens. They begin to pull in more material from their orbital path, sweeping up smaller debris in a process called runaway growth. The largest of these bodies, the protoplanets, dominate their neighborhoods, clearing their orbits and continuing to collide and merge in a series of giant impacts that can be both creative and catastrophic. The architecture of the final system is a record of this violent youth. Gravitational scattering, where one massive body flings a smaller one into a new orbit or out of the system entirely, is a common event. Planets can migrate inward or outward through interactions with a gas-rich disk or with other planets, reshaping the entire system's layout in its first 100 million years. This migration is thought to be the reason we find so-called hot Jupiters, gas giants orbiting incredibly close to their stars. They likely formed farther out and spiraled inward, a journey that would have disrupted or ejected any smaller, Earth-like worlds in their path. The final arrangement of planets is a delicate dance dictated by orbital dynamics, the rules of motion set by gravity, and the conservation of energy and angular momentum. These rules determine the spacing, the shape, and the long-term stability of orbits. One of the most fascinating patterns to emerge from this gravitational choreography is the phenomenon of orbital resonance. This occurs when the orbital periods of two bodies are in a simple integer ratio, like 2 to 1 or 3 to 2. Picture two runners on a circular track. If one runner laps the other exactly every 2 of their own laps, they are in a 2 to 1 resonance. They will meet at the same point on the track over and over again. In space, this repeated, predictable gravitational tug can have profound effects. It can be stabilizing, like the resonance that locks Neptune and Pluto in a 3 to 2 dance, ensuring they never get too close. Or it can be violently destabilizing, clearing gaps like the famous Kirkwood gaps in the asteroid belt, where any object whose orbit resonates with Jupiter's powerful gravity is quickly ejected. Our own solar system is a testament to this intricate gravitational engineering. the orbits of the giant planets are thought to have shifted in a grand tack, a slow migration that scattered comets and asteroids but ultimately settled into a remarkably stable configuration that has persisted for over 4 billion years. But our system is just one possible outcome. The discovery of thousands of exoplanets has revealed an astonishing diversity of architectures that we never anticipated. We have found solar systems with multiple stars, planets orbiting in opposite directions, and super-Earths, worlds larger than our own but smaller than Neptune, which have no direct counterpart in our cosmic neighborhood. This incredible variety tells us that while the fundamental physics of accretion and gravity are universal, the outcomes are wonderfully chaotic and unique. Each planetary system is a frozen snapshot of its own dynamic history, a history written in collisions, migrations, and gravitational embraces. And within these stable, long-lived systems, on the surfaces of rocky worlds that survive the chaos, the universe gains a new capability. It is here, on these stable platforms orbiting stable stars, that the complex chemistry forged in stellar furnaces can interact, persist, and perhaps, under the right conditions, begin to organize in ways that are not just physical but truly alive. The universe builds with predictable forces, but it dances to a rhythm of exquisite uncertainty. Even the stately orbits of planets and stars, governed by Isaac Newton's clockwork laws of gravity, hold a deep secret. They are not eternally predictable machines. When three or more bodies move under their mutual gravitational pull, something profound happens. The system becomes chaotic. This does not mean random. The laws are perfectly deterministic, meaning if you knew the exact position, mass, and velocity of every object at one moment, you could, in theory, calculate their future forever. But in practice, you cannot. The tiniest, most imperceptible difference in your starting measurement, a variation smaller than the width of an atom, will grow exponentially over time. That microscopic uncertainty blossoms into a completely different cosmic future. This is the hallmark of chaotic systems, often called the butterfly effect in celestial mechanics. It places a fundamental limit on our ability to forecast the distant fate of any complex gravitational system. Consider our own solar system. We can predict eclipses and planetary positions with stunning accuracy for thousands of years. But try to project the motions of all the planets, moons, and asteroids over billions of years, and the veil of chaos descends. Minute gravitational tugs, the subtle influence of a passing star, or the slow loss of mass from the sun, all act as seeds of uncertainty. Over deep time, these seeds can grow into dramatic events. A planet's orbit might slowly stretch into a more elliptical path. A moon could be ejected from its planet entirely, cast adrift into interstellar space. Two asteroids on seemingly stable paths might, after millions of years, find themselves on a collision course because of a long-forgotten gravitational nudge. This chaotic behavior is not a flaw in the laws, it is a direct consequence of them. It means the universe is inherently creative, even within a framework of perfect rules. On a grander scale, the orbits of stars within a galaxy are also subject to this chaotic mixing. While a star generally follows a smooth path around the galactic center, the combined gravitational pull of billions of other stars, dark matter halos, and spiral arms acts as a constant, subtle perturbation. Over many orbits, these perturbations can gradually change a star's path, scattering it from one region of the galaxy to another. This stellar diffusion helps to blur and mix the populations of stars, ensuring that the galaxy is not a static collection of fixed orbits, but a slowly churning, dynamic entity. This inherent unpredictability within a deterministic framework is one of the most fascinating truths of celestial mechanics. It reminds us that universal forces do not guarantee simple outcomes. Complexity and surprise are emergent properties, baked into the mathematics of motion itself. Yet, from this local tapestry of chaos and chance, the universe somehow weaves a pattern of breathtaking order on the largest canvas of all. From the chaotic orbits of individual stars, a breathtaking order emerges when we step back to see the entire cosmos. The universe is not a random scattering of galaxies, but a tapestry woven on the grandest possible scale. This is the cosmic web, the final and most majestic structure in all of nature. It is a vast, three-dimensional network of delicate filaments, immense walls, and sprawling, nearly empty voids stretching across billions of light years. Picture the universe as a colossal sponge, where the solid material forms a complex, interconnected lattice, and the holes are cavernous spaces of profound emptiness. This is not a metaphor, it is the actual architecture of reality. The galaxies we see are not sprinkled like salt across a dark tablecloth. They are strung along these luminous threads, gathered into dense, glittering knots where filaments cross, and are almost entirely absent from the dark voids in between. This web is the ultimate expression of gravity's patient, large-scale work. Its story began with those faint quantum whispers from the inflationary epoch, the tiny ripples in density frozen into the infant cosmos. Dark matter, responding only to gravity, acted first. It collapsed along the lines of these ripples, forming an invisible skeleton, a gravitational blueprint of valleys and ridges. Ordinary matter, the gas that would become stars and galaxies, then flowed like water into these dark matter valleys, pooling along the filaments and at the intersections. Over billions of years, this process sculpted the web we observe today. The dense knots where multiple filaments meet are the homes of galaxy clusters, the most massive gravitationally bound structures in the universe, containing thousands of galaxies. In contrast, the voids are incomprehensibly vast regions, spanning hundreds of millions of light years that contain almost no galaxies at all. They are the cosmic deserts, the empty spaces between the glittering cities of the web. This structure is more than just a pretty pattern, it is a fossil record. The specific way the web is woven, the thickness of its filaments and the size of its voids, encodes vital information about the universe's ingredients and history. It tells us about the nature of the dark matter that forms its backbone, whether it is cold and slow-moving or slightly warm. It reveals the influence of dark energy, which, by accelerating the expansion, affects how quickly the web can grow and evolve. Most powerfully, our supercomputer simulations of cosmic structure formation, which input the laws of gravity and our best estimates for dark matter and dark energy, successfully reproduce this exact web-like pattern. When we compare the simulated universe to the one we observe through massive galaxy surveys, they match. This is one of the strongest confirmations of our entire cosmological model, from the Big Bang to the present day. The cosmic web is the final, magnificent outcome of every force and phenomenon we have explored. It is the stage set by inflation, built by gravity, framed by dark matter, and now being stretched and pulled by dark energy. Every galaxy, including our own Milky Way, is a passenger on this vast network, flowing along gravitational rivers toward the dense clusters over cosmic time. It represents the universe thinking in patterns, finding structure in chaos, and building a connected whole from countless individual parts. As we look out and map this grand design, we are reading the signature of creation itself, written across the sky in the language of gravity and light. From the quantum whispers of the beginning to the vast cosmic web of today, a single truth emerges. These 30 forces and phenomena are not a random list of cosmic facts. They are the moving parts of a single, breathtaking engine, an interconnected machine of staggering complexity and profound elegance. The story we have traced is not a collection of isolated events, but a continuous chain of cause and consequence, where each chapter sets the stage for the next. The Big Bang provided the raw energy and the starting moment. Cosmic inflation then acted as the master sculptor, ironing out the wrinkles and, most crucially, amplifying quantum uncertainty into the gravitational seeds for all structure. From those seeds, gravity and dark matter began their patient, collaborative work, drawing together the first clouds in the darkness. The fundamental forces provided the rulebook, the strong nuclear force building stable atomic nuclei, the weak force allowing for transformation, and the matter-antimatter asymmetry, and electromagnetism weaving the tangible world of light and chemistry. Within the first stars, nucleosynthesis ignited, beginning the alchemical transformation of simple hydrogen into the elements of life. Their spectacular deaths in supernova completed the process, scattering those elements across space and triggering new rounds of star birth through feedback loops both gentle and violent. Magnetic fields channeled this chaos, relativistic jets carved through galaxies, and the silent, persistent pressure of dark energy began to dictate the ultimate tempo of expansion. Every spiral arm, every planet, every black hole, and every distant quasar exists because of a precise sequence of dependencies. The radiation pressure that balances a star relies on the nuclear fusion happening in its core, which itself depends on the strong force overcoming electromagnetic repulsion. The gold in a wedding ring was forged in a neutron-star collision, an event made possible by the gravitational collapse of a massive star, which was itself born from a molecular cloud whose collapse was triggered by a supernova shockwave from a previous generation. This is a universe of endless recursion where the output of one process becomes the essential input for another. Seeing this interconnectedness changes our understanding. We cannot truly grasp dark energy without appreciating the gravitational structures it is stretching apart. We cannot comprehend the cosmic web without acknowledging the quantum fluctuations that seeded it. The universe operates as a holistic system, a dynamic equilibrium where push and pull, creation and destruction, are in a constant, delicate dance. This synthesis reveals a cosmos governed by a surprisingly small set of physical laws, but the interactions of those laws produce an infinite tapestry of complexity and beauty. To understand our place in this story is to see that we are not merely observers of a finished product. We are a dynamic expression of the engine itself, our very atoms forged in stellar furnaces, our planet assembled from the debris of ancient explosions, our existence made possible by a broken symmetry in the first second of time. We are both a product of the cosmic engine and a means for it to become aware of itself. This perspective prepares us for a final, reflective question, one that brings our journey from the forces of creation full circle to the meaning we find within them. The cosmos is not a distant spectacle, but a story we are woven into at the most fundamental level. From the quantum foam to the cosmic web, its entire evolution is a narrative written by just 30 fundamental architects. We have traced how titanic forces like gravity and dark energy sculpt the ultimate fate of the universe across billions of years, while transformative phenomena like nucleosynthesis and reionization fill that vast canvas with light, chemistry, and complex structure. Each scientific discovery, from the faint afterglow of the Big Bang to the faint tremor of colliding black holes, peels back another layer of this grand mystery. What it reveals is a cosmos of breathtaking duality, profoundly ordered by elegant mathematics yet vibrantly dynamic in its expression, predictable in its laws yet beautifully chaotic in its outcomes. This is not an abstract history. It is your personal origin story, the calcium in your bones, the iron in your blood, the oxygen in your lungs. Every atom apart from the primordial hydrogen was forged in the heart of a long-dead star. You are literally stardust, assembled over cosmic time by the very forces we have explored, gathered on a world built from the ashes of stellar explosions. This connects us to the universe in the most intimate way possible. As the astronomer Carl Sagan so poetically expressed, we are a way for the cosmos to know itself. Our curiosity, our science, Our very consciousness is the universe turning its gaze inward, beginning to comprehend its own magnificent machinery. So the next time you look up at the night sky, let that feeling be different. See not just points of light, but in points of an epic journey. See the grand spiral of a galaxy and recognize the dark matter scaffold holding it together. See the faint smear of a distant nebula and know it is a stellar nursery powered by the same nuclear forces that warm our planet. Which of these cosmic drivers resonates with you the most? Does the patient power of gravity, the enigmatic push of dark energy, or the creative violence of a supernova capture your imagination? Share your thoughts in the comments below. I would love to hear which part of this grand engine fascinates you. If this journey through the fundamental forces of reality expanded your perspective, please subscribe for more deep dives into the mysteries of space, time, and existence. Thank you for exploring the engine of creation with me.